Okay, I got a request to touch up on lesson 124, or I'm sorry, 121.4. Um, this is a parallel circuit, heavy lesson, and I want to look at sort of this bunch of questions here, number 2 through number 8. Okay, and this is a tough set of questions. But I think a key here is, I don't like to look at this is one question, that's one question, that's one question. That's a lot of work for one question. But rather, let's look at this whole bunch, number 2 through 8, as sort of one big question. Because to solve a lot of these, you're going to sort of inadvertently need to solve the others. So let's kind of look at this as one big piece here. So, first thing I want to talk about is what kind of circuit are we dealing with, right? We have 3 pieces of equipment: a washing machine, shirt press, clothes dryer. They're all fed from this one 2-pole breaker out of this panel, which is 120, 240 volt. If I have a 2-pole breaker in a panel, and it's in this case 120, 240, that 2-pole breaker is going to be the higher of the 2 voltages always. So we're feeding all this on a 240 circuit. They show us here these are connected in parallel. Anytime you have circuits plugged into a building, in general use instances, it's always going to be parallel connected. But in this case, they show us that pretty good. So, and then they give us the values of all these pieces of equipment. So let's jump over here. I've got sort of a fancy version of the grid system that we use to sort of talk about this. So first thing, our source voltage. They got to tell us that, and they tell us it's 240 in this case. Some other info we know, and I'm just going to pull this right out of the question. The voltage of the washer, it was 220 volt and 7.2 amps rated. Shirt press was 230 and 1800. And then we can say the dryer, 250 and 5000, right? So that's all of our rated voltages. So right off the bat, there's only a couple moves we can make here. The first one, always a good one. Let's enter the source voltage for the total voltage. Doesn't matter what kind of circuit it is, we can always do that. Happens to be in a parallel circuit, E total equals E1 equals E2 equals E3, which means all of these circuits here equal, or all of these boxes here equal 240, right? So in this case, we can literally copy and paste 240 all the way across. And we can do that because of this rule pertaining to parallel circuits, right? So the next thing we got to do, the only thing we can do, is we need to find the fixed resistances of all these pieces of equipment, because we're not operating any of them at their rated voltage. So they're going to give us something other than their rated amperage or wattage, right? So let's find fixed resistance. We're just going to use Ohm's law. We know for the washer we have volts and amps. We need ohms. We can say E divided by I equals R. When we do that, we should get 30.556. Over here on the shirt press, we have volts and watts. If we are looking for ohms, we say E squared divided by P. E squared divided by P, in that case, should give us 29.389. Same story for dryer. E squared divided by P, we're going to get 12.5. Okay, so now we have all of our resistances. That's almost always your first or second step in all these problems. I can't stress that enough. So the next thing, now we have some options. We could find total resistance using this formula. However, as I told you, I despise this formula, so I try to avoid it wherever possible. And in this case, we can avoid it. We're going to work around it. We do have 2 values in every column, or in these 3 columns, I should say. So we could use Ohm's law to find the other 2 values easily, right? I happen to like amperage. Let's go for amperage. It doesn't really matter which one you want to do next. In all cases, we have volts and we have ohms. We're looking for amps. So we can say E divided by R equals I. E divided by R is going to give us I, which in this case is 7.855. In the next case, we're going to say E divided by I once again. We get 8.166 amps. And lastly, E divided by I once again for the dryer, we're going to get 19.2. Okay, so now we have even more options. I want to go for total amperage. Again, it doesn't really matter which order you do these in at this point, but we can actually use this rule to find our total amperage, right? You can say I1 plus I2 plus I3 equals I total. We can add all these guys up, When we do that, we should get 35.221, right? So now we have a ton of options here. We have a couple moves in either direction. Let's go ahead and fill out these wattage values using Ohm's law again. I happen to like E times I gives us P. So in this case, we have 1885.091. Again, E times I is going to give us 1959.924. And lastly, E times I, the last column, gives us 4608. So now we can find total wattage. We can say P total equals P1 plus P2 plus P3. Or in other words, add these three up. And we come up with 8453.015. Okay, and now we can sort of do this big nasty total ohms without using this formula. We can essentially use Ohm's law at this point, right? So we're looking for R. Let's go ahead and do E divided by I. E divided by I in this case should be 6.814. Okay, so now we can essentially take these values, go back to those questions. All of those questions, one of these values is going to be your answer. Before we do that, let's just talk about the results here, right? Make sure everything makes sense. So the washer was rated 220. We're actually going to operate it at 240, a little bit higher voltage. So look what happens to the amps. It was 7.2, but since we're operating it higher, the amperage actually goes up. Higher voltage equals higher amperage. Same story on the strip press. It was rated 230, should have put out 1800 watts. We're actually operating a little bit higher at 240, puts out 1959 watts. So the watts go up a little bit. Makes sense, right? Conversely, on the dryer, it's rated 250. It should be 5,000 watts. We operated at 240 instead, and the watts goes down a little bit to 4608. So all those values increased or decreased appropriately, as we should expect. Another little check I like to do, in a parallel circuit, your ohms, total ohms, should always be the lowest resistance value in the circuit. Reason for that is each one of these loads lets a little bit of current through, and to add them all up, it lets more and more current through, so the total resistance, more current can flow because there's less resistance on the total circuit compared to any one piece. That's kind of confusing to think about, but if you don't understand that, just keep in mind the total resistance should always be the lowest value in a parallel circuit. It's a nice little check at the end, right? All right, so let's jump back and start filling in some answers here. So number 2, they want to know the voltage dropped across the washing machine, which is a fancy way to say the voltage applied to the washing machine. Or what's the voltage of the washing machine element, or element 1. Plain and simple, in a parallel circuit, every question about voltage should be the source voltage, because voltage is equal everywhere in a parallel circuit. So we can say 240. No doubt about it. Okay. Next one here, number 3. The resistance of the clothes dryer is blank ohms. So really what they're saying is, go back here to the clothes dryer. What'd you punch in for your resistance value? 12.5. We figured that out right away using Ohm's law with the rated values, right? So 12.5. Number 4. The circuit supplies blank total watts of power to all 3 loads. In other words, what's the total wattage of this circuit? Come back here, find our watts, total 8453.015. And they, for some reason, round off all the decimal places. I don't know why they decided to do that there, but whatever. And again, we have to excuse some rounding differences. That's negligible in cases like this. Number 5, the resistance of the washing machine is blank ohms. So again, just like question number 2, we come back here, washing machine resistance 30.556. Again, we found that using Ohm's law way back in the beginning, right? 30.556. Okay, good. Number 6, with all loads operating, the current flowing through the circuit conductor connected to the upper terminal in the circuit breaker is blank amps. That's the toughest question in the bunch, in my opinion. So let's save that till the end. We'll come back to that one. It's not as tough as it seems once we break it down. Number 7, the current drawn by the shirt press is blank amps. Well, here again, come back to your little chart. Shirt press, amps, 8.166, right? So you can see, I mean, we would have roundabout solved almost all those values anyway. So I almost always start filling out a chart like that when I see a problem like this, because it also helps you sort of document your previous answers. You can see how work you might have done in this question would probably come in handy for this question, for example. So it's good to do that grid method, sort of document your steps and your answers as you go, because you'll probably have to refer back as you go through all this. So the last one in this bunch, the current flowing through the clothes dryer is blank amps. Once again, no big deal. We can say, okay, clothes dryer, current 19.2. There we go. We like it. So let's go back to question number 6. Okay. So with all the loads operating, the current flowing through the circuit conductor connected to the upper terminal on the breaker is blank amps. I've drawn this out. Okay. I've sort of color-coded everything too. So red is your highest amperages, and then it gets down to orange to yellow to green, and then sort of the greenish blue is your lowest amperages. So you can tell sort of where most of your amps are flowing. So let's actually start way back out at the end here. So the dryer is 19.2 amps. So the only amperage that's out here is the amperage that's flowing through the dryer. As we get back and hit this shirt press, now, the shirt press has 8.166, dryer 19.2. So it stands to reason this wire here and this wire here, because the press and the dryer are on the load side of it, these two sections of orange wire see the load of this plus this. And as we break that back even further, now we add in here the washer load, which is 7.855. So these wires here see the load from all three elements, or in this case, it has to be the total amperage of the whole circuit. So the question is, what's the amperage on the upper hot leg coming off the breaker? So if we're coming off the breaker, right away we have to know that we're finding total amperage, right? And I think, maybe some people would sort of be tempted and you question, well, should I divide that in half, and half of it's on this leg, half of it's on that leg? But, plain and simply, no. I think that's a bigger discussion, exactly why that is. But I think or at least I hope this sort of helps break it down. And again, you just really have to think of each of these elements as being additive. So short answer, our answer for that question needs to be 35.221. Right, or 35.22 in this case. And I want to circle back. So, I did mention the lowest resistance in a parallel circuit should always be total resistance. Because think about it. This resistor lets a certain amount of current through. This one lets a certain amount through. And this one lets a certain amount through. And they all kind of add up. In other words, if you thought of this as water pipe, you had a little 1-inch pipe, a 1-inch pipe, a 1-inch pipe. They all let some water through. And their combined effect on the other side is, 3 total inches, however you want to look at that. But they all sort of combine to let more and more current through. Higher current means less resistance. High resistance resists current flow, so it's low current. So again, we're really getting down the rabbit hole here, but some nice checks and balances for you guys. So I hope that's helpful. You're going to see like these questions here. Treat them the same way. Take that grid method. Just start filling out your grid. I can see here there's, right away there's 1, 2, what else do we got here? 3, so there's 3 questions just on that one scenario. So treat those as one big question. Don't look at them as 3 separate questions. I think that's really daunting. So anyway, hopefully that's a help. If not, reach out. We can do this all day long. But again, hopefully that was beneficial and gets you guys out of the woods here.